Hello and welcome back to my channel. Today we will be talking about energy. Well, energy is basically, you may wonder like what is energy? You might hear the term energy a lot in your everyday life when you're talking about energy, like, oh, I have energy to do this, or I don't have that much energy today. Well, what is energy in terms of physics, right? When you're referring to energy in the terms of physics, energy basically means the ability to do work. Not work as in like your homework. Again, work is into what we stated in the previous section of this unit, right? Work as in like the force over a certain distance. So it's the ability to do work. So now there's certain types of energy that we can work with, right? The first type of energy that we have is kinetic energy. Well, what is kinetic energy? Kinetic energy is something that every moving object possesses. Every time something moves, it has kinetic energy. Like you throwing a baseball has kinetic energy. You walking, you have kinetic energy. Anything that moves has kinetic energy. What is helpful for? Well, kinetic energy can really help describe where we get a lot of our formulas and equations. Pardon me, where we get a lot of our everyday activities from. We can determine the kinetic energy of many things, of anything that moves, really. So that's why it's really important that we know how to use kinetic energy. It's really applicable to the real world. The equation for kinetic energy, the equation is EK is equal to 1/2 mv squared. And remember that our symbol is simply just EK. Why don't we have a vector on this v right here? Well, again, just like on our last video, we talked about how energy is a scalar. So energy won't have actually any vector signs. We can actually just completely just drop the vector signs because we're not really working in vectors, we're working in scalars right now. So you might be wondering, how did we really derive this formula for energy? How did it come about and where does it really come from? So if you think back to our previous lesson about work, we talked about work right here. Work is equal to force times delta D. Delta D being displacement and then force. Well, what else can force equal to? Well, force is also equal to mass times acceleration. Okay, so let's try to sub this into here. Let's see what we get. We get work is equal to ma delta D. Okay, now we're getting somewhere. We have m in the equation, so much we have that up here. Okay, what else can we do? Well, we can look for what acceleration can equal. Well, we can use the formula. Well, acceleration can equal many things. Acceleration can equal v2 minus v1 over delta t. There's a couple other formulas that we can use for acceleration, but another one that we can use is v2 squared is equal to v1 squared plus 2a delta d. Now if we rearrange this equation, we end up with, well, we can minus out our v1 squared. We can divide by 2 delta d, and you're left with v2 squared minus v1 squared over 2 delta d is all equal to our acceleration. Now that we have this, we can sub this in for our a. Now we get work is equal to mass times v2 squared minus v1 squared over 2 delta d times delta d. And if you notice here, actually our delta d's will just cancel out, and you'll be left with simply work is equal to mass times v2 squared minus v1 squared over 2 delta d. And from here, you can assume that, pardon me, now you can get work is equal to 1/2 mvf, so our final, or mv2 squared minus 1/2 mv1 squared. And that's how we get our different works. So we can either get, we know that our total work is going to be, for kinetic energy, is going to be initial minus final, right? So, but we know that this is technically equal to energy is EK is equal to EK2 minus EK1 for our total energy, right? We know we can understand that. And that's how we really derive the formula for energy. From all of this, we can understand that our energy formula just for energy alone is just 1/2 mv squared. So now that we understand that and what we can derive from energy, now we can try to move into some sample problems and use energy and kinetic energy in some real world context. Okay, now we have a sample problem in front of us. Something I want to clarify from before that I might not have properly explained up here. When we have EK is equal to EK2 minus EK1, this is also equal to delta EK. And delta EK is equal to work. That's something you have to keep in mind. Work is equal to delta EK, and delta EK is equal to EK2 minus EK1, which is what we derived up here. And something you have to also keep in mind when we're doing this is that when we found the equation for energy, what the people did is they assumed the first initial was at rest. That's how we got 1/2 mv squared is just equal to EK. So I apologize for probably not explaining it as clearly as I should have, because delta EK is equal to EK2 minus EK1. So I apologize for that. Let's get into the question now. So calculate the kinetic energy. Calculate the kinetic energy of a 150-gram baseball that is traveling towards home plate at a constant speed of 35 meters per second. So this question, let's get straight into it. So it says that the mass of the baseball is 150 grams. Well, we already know that we have to work in kilograms. So we have to convert this over to kilograms. So 150 grams to kilograms is simply 0.15 kilograms. Now that you have kilograms, you can go into the next part that is traveling towards home plate. So at a constant speed, so we know that the velocity is just 35 meters per second. And that's pretty much all we really need. Now we can just go straight into our analysis. We know that it's going to be EK is equal to 1/2 mv squared. And we just go into our solution. EK is equal to 1/2 m, which is 0.15 kilograms, and 35 meters per second squared. Now we can just go straight into this. So 1/2 times 0.15 times 35 squared, which ends up just being EK is equal to 91.875 joules. Round off to two significant digits because we have 2 here and 2 here. So EK is equal to 92 joules. Now that we're done that, we can move on to the next question. The next question is a little more tricky. So it's a 165-gram hockey puck is initially at rest. Initially at rest is pushed by a hockey stick on a slippery horizontal ice surface by a constant horizontal force of magnitude 5 newtons. Assume that the ice is frictionless. What is the puck's speed after it has moved 0.5 meters? So let's break this down. So we know that our mass is going to be 165 grams. Convert this to kilograms. We know that's going to 0.165 kilograms. We can always do a form of 1. From here, though, we know that the horizontal force, so F, is equal to 5.0 newtons for this simple equation. And we know that the speed, the delta D, is 0.50 meters. And we're looking for the speed, right? What is the puck speed after it has moved? So we're really looking for our velocity. So what are we going to do here, though? Because we don't have much to go off of. We can go EK is equal to 1/2 mv squared. We have mass, and we can but we don't have EK either. So that doesn't really help us. So let's try to think back on what we do have. Well, let's think of some of the formulas we have. We know that work is equal to force times delta D. Okay, we have a force and we have a delta D. So let's use that. So you know work is just equal to force times delta D. So we can use this equation. But how is this going to help us? Well, if you think back to what we had before, work is equal to delta EK. Remember how we derived this formula up here? And we showed how work is equal to delta EK. Well, how is that helpful here? Well, if we rearrange this and we write work is equal to EK2 minus EK1. And instead of work, we write force times delta D. So force times delta D is equal to EK2 minus EK1. And we know actually a piece of information that we may have missed is that it's at rest. So we know that V1 is equal to 0, and we're looking for really V2. So if our V1 is 0, this would be force times delta D is equal to 1/2 mv2 squared minus 1/2 mv1 squared. Well, V1 is just 0, so this just drops out, so that zeroes out. And we have force times delta D is equal to 1/2 mv2 squared. And we're looking for V2, so we just have to rearrange. So times by 2, divide by m, and square root. So we have force times delta D times 2, divide by m, take the root, is just equal to V2. And now we can go into our solution. Our solution is simply going to be 50 newtons times 0.50 meters times that by 2, divide by mass, which is 0.165 kilograms, take the square root, and we'll get V2. So now this is all just calculator work, but let's calculate what we get. 0 times 2, 0.165. So you end up getting 17.4 meters per second. Pardon me, let me rewrite this. 17.4 meters per second is equal to V2. And let's round off to 2 significant digits since we have 2 everywhere else. So we have 17 meters per second is equal to V2. And that's basically how we work with kinetic energy. That's the first part of our energy lesson. The next part, we're going to get into another type of energy and how that energy applies to our real life world. So I'll see you in that part. Okay, now let's talk about the other type of energy, which is gravitational potential energy. So first of all, what is potential energy? Potential energy basically refers to a stored form of energy. So a stored form of energy. A form of energy that everything might have but may not be using at a time. So that's just something that you will often hear. You'll often hear like potential energy of an object. That just basically means a stored energy that can be used, but it isn't necessarily being used. So now let's talk about gravitational potential energy. Gravitational potential energy refers to energy due to gravitational force on an object with the height. So let's write that down. Energy due to gravity. Due to gravitational, force due to gravitational force and object's height. Now that we have that, let's understand what that actually means. Well, gravitational potential energy, what is the equation and symbol for it? So the symbol we use for gravitational potential energy is basically just EG. EG is the symbol. What's the equation? Well, the equation that we use for gravitational potential energy is simply just EG is equal to mgh. And the units we work in are again going to be joules. Now, why or how did we get mgh as our formula? Well, if you think back to what we talked about previously, if we're holding a book up, maybe say in the air from a reference point, maybe say, let's say this is a table right here, and you're holding a book up in the air. And if this is a free body diagram, it's going to have a force normal and a force of gravity. So assuming that you're not moving the book and the book's stationary, well, the force normal and force of gravity are just going to equal each other. So Fn is going to equal mg. And now that we think back to what work means, work is again equal to force times delta d. And if our forces are all balanced and Fn is equal to mg, well, that basically means that we have mass times gravity right here, which is right here, and we have just some height that's lifted off of maybe 10 meters or whatever height, and that will give us, if we multiply all these together, we'll get our potential energy of an object due to gravity. So gravitational potential energy, that's what we get. Now we can look at the sample problem right here and try to just use what we learned to work it out. So what is the gravitational potential energy of a 48 kilogram student at the top of a 110 meter high drop tower relative to the ground? So we're assuming that the student is height is relative to the ground, so anything from the ground up. So we can go ahead and work in this question. So we're looking for the potential energy. We know the mass is simply 48 kilograms, and their height is 110 meters. This is something similar to maybe a high drop tower you'll see at like a museum, at a carnival. You'll see maybe it'll be out all the way up here, and this distance up here is 110 meters. So we can calculate their gravitational energy when they're all the way up there. So something we also have is we'll always have g. Well, we always know what g is. It's 9.80 meters per second squared. And now we're going into our required to find, which is simply EK. We're looking for what EK is. Now we can go into our analysis. And analysis, we can go, not EK, EG. We're looking for gravitational. So EG is equal to mgh. And we have m, we have g, we have h. So now we can go straight into our solution. Now we can go EG is equal to 48 kilograms times 9.80 meters per second squared times the height, which is 110 meters. And now we can just solve this. So 48 times 9.8 times 110 is equal to 51,744 joules when we round to two significant digits, because there's two is the lowest amount, so we get is equal to 5.2 times 10 to the 4 joules. That's basically our gravitational potential energy. And that is all of energy. Really, all these things that we work in with energy, they're really just like using these formulas and just trying to manipulate the formulas, just like most of what physics really is. And another term you might hear is mechanical energy. That's basically the total kinetic and gravitational potential energy. So mechanical energy, you may see it in the textbook. That just means kinetic plus gravitational. That's just what it means. It's just like the total of both. So that's just something to keep in mind when you're working through your fun work. But I hope this video helped, and just make sure you keep practicing. Really, all of this is really practice. And remember that, again, that I talked about, work is equal to delta EK. That's what we want. Work is equal to EK2 minus EK1. That's a topic that is going to be used, and that's something that we can use all throughout our physics work. But I hope you enjoyed this video, and remember, physics rocks.